EET105 Inductors, example problem 44. This is inductors in series and parallel. Find the mathematical expressions for the voltage V sub L and the current I sub L following the closing of the switch. So you can see that you have a voltage source here going into this resistor R1 10K, and then you have R2 20K going to ground, and then there's a switch. Then you have L1, which is in series with L2 and L3 that are in parallel. So how do you solve this problem? Well, first thing is, since you have these two resistors that are in a neither series nor parallel configuration with everything else, you need to find a Thevenin equivalent. So again, you take this out of the equation. This is your A and B, because these are, the items that you want to solve for. So you take them out, and then you just look at this circuit this way. This is your terminals A and B. So our Thevenin, when you short out this 20 volt resistor or 20 volt source, is going to be R1 in parallel with R2. So 10K in parallel with 20K equals 6.67K. And then you put the voltage source back in. You're looking for the voltage across R2, which you use a voltage divider. So 20K times 20 volt divided by 20K plus 10K equals 13.33 volts. So now you have your simplified circuit, which is just E Thevenin in series with R Thevenin, and then you have this inductor circuit, this network right here to deal with. So how do you do that? Well, same as resistors, you can find the equivalent inductance of all three of these together, which is going to be these two in parallel, the 4.7 and 10 in parallel, which is this, and you add the 3 to it. So 4.7 times 10 is 47, divided by 4.7 plus 10 is 14.7, ends up being 33.197 henries. By the way, these are really large values. Usually it's milli or micro henries. Inductors usually aren't in henries. I think they just did it for simplicity for calculation. And your total inductance ends up being 6.197 henries. And then tau equals your total inductance divided by your Thevenin equivalent resistance, which ends up being 0.93 microseconds. So then you plug that into the charging equation for V sub L, which is this, there's storage, this equation, and you get 13.33 times e to the minus t divided by 0.93 milliseconds. And then again, same thing, you use the storage equation for I sub L, you plug in your values for E Thevenin and R Thevenin, and then do the math, and you get this simplified version of I sub L. So as you can see from this equation, it's going to say sketch the waveforms. So I2 ends up maxing out at 2 milliamps after 5 tau, which is 4.65 milliseconds. And then V sub L maxes out at 13.33, and it decays down to 0 after 5 tau. Similar thing. And then part C is asking you to determine the mathematical expression for the voltage V sub L3. So this voltage just across here, following the closing of the switch, and sketched a waveform. So V sub L3, this is just a ratio. So you have, it's kind of like a voltage divider situation. So it is going to be, this is the equivalent voltage or inductance, of these two in parallel is at 3.197, which is what we calculate up here. and then this is the 3 Henry, which is L1. So you just do a ratio, 3.197 divided by the total of both is 0.52 of V sub L, so it's roughly half. So then you take the V sub L equation, multiply it by 0.52, and this is what you get here. And it's just saying, it's just asking you to for the expression and sketch the waveform. The waveform is going to look exactly like this waveform, only that value, instead of the 13.33 value, it'll be the 6.93 value. And I also drew this circuit and every circuit just as it was, just to show you. When I tried to put these two inductors in parallel, it said error, check circuit topology. Okay, so it will not even allow you to draw it just like this. It showed this up in red. So what I ended up doing was drawing it with this 3.197 Henry inductance, the equivalent of the two in parallel, and then did it that way and uh, got my graph, which again is very similar to the values that we found here. And I'll show it to you in every circuit here. So we turn the circuit on. You can see that there's already current flowing through this resistor here because there's a path. And this is a loop. And then we close it like that, and this is what we get. You can see that this the current ends up being about 2 milliamps. I'll let it run a little bit longer. So it's 2 milliamps. It goes up from 0. So it starts off as an open circuit, ends up as a short. And then the voltage across both of these inductors was 12.7 max, and it decays down to 0. And then this voltage ends up being 6.53, which is roughly 0.57 times this voltage here.